Yes.
Okay, so here's the problem we were having some issues with. There's a solution down there, but let's take a look here. Consider the following function, 6 cosine pi of pi x over root x. What conclusions can be made about the series and the integral test? And we got these options. Let's just go through the options. So the integral test can be used to determine whether the series is convergent since the function is positive and decreasing. Positive and decreasing. Well, cosine, first of all, we know that here, and actually, let's snip this in our, let's see here. This is 11.3. And let's just grab this and take a look at it over here. There we go. Okay. Okay, so first off, positive and decreasing. Well, I don't know. First off, cosine, if we're looking at that, that alternates from -1 to 1. And, well, the whole top, we got a 6 in front. So actually, it's going from -6 to 6 constantly. It's going positive to negative, positive to negative. So, I mean, I guess we could start plugging in values. I mean, because we're going by integer values of pi. So if we really want to be sure, we would want to go ahead and go, well, what? Cosine of 1 pi, 2 pi, 3 pi, 4 pi. What is it doing? That's not cosine. So, oh, here, I tried turning something on. Let's see if it works. Nope, that didn't erase it. What's up with that? Whatever. All right. Let's see here. So, anywho, this is 2 pi. This is pi. That's 0. And we could go a little bit further if we want. 2 pi, 3 pi, and right there would be 4 pi. All right. So anyway, what's happening at integer values of pi? When we're doing cosine, it's going from, let's see, first starts off at, well, that whole top part, if I'm looking at this whole thing, would be 6. Then it would be -6, and then it would be 6, and then it'd be -6, and then it'd be 6, and then -6. Okay, so I'm looking at this top part. It's just alternating back and forth between 6 and -6. No matter what this thing is doing at the denominator, obviously that's getting bigger and bigger. So the integral test can be used because it is positive and decreasing. First off, it's not always positive. Secondly, it's not decreasing. It's increasing and decreasing constantly. Because, you know, it's this kind of thing, and then we keep dividing it by a larger number. So you divide something by a number larger and larger, I think it would start off kind of like this, and then get closer and closer and closer. You know, just my intuition here would say that's kind of what it's going to look like. Something like that. If we would graph it as a function, of course, they'd be dots, really. Okay. So that one would be no good. Bam. And now jumping ahead. So actually, Karen Deep, I should have asked you, do you have any idea maybe where you might have had some trouble with this? It's like something I should start on?
And not necessarily.
Okay.
I mean, I know how to do it now.
Okay. All right. Okay, so this is the way I would do it. I'll just go through them. Integral test can be used since the function is not positive. Oh, that's just wrong, because integral test says it has to be positive and decreasing for the integral test to work. So that's no good. The integral test can be used. And we already know, no, it can't be used, so we're done. It cannot be used since the function is not positive and not decreasing. Oh, well, there, yeah. I would say it's not decreasing because It's increasing and decreasing all the time. There's not information. No, we're good. So in this case, that would be it. And this answer here is pretty much stating when we can use it. So there that one is. And again, I'll take a look at those submissions and see if something funny was happening.
Okay, thank you.
No problem. Okay, so before we get going, let you guys know my plan. It's really simple today. I was going to do a root test example. We haven't done one with you and me. Super easy. So we'll do a root test. Then go through the review. Just pick some problems here and there. See how many we can do. And if there are certain problems you would like to be messing with, then we will mess with those in particular. And then, anything else. So first things first, questions. We took a look at this guy. Is there something else you guys want to look at? Going once? Going twice? I guess not. All right. Well, then, in that case, I want to do a root test example. So that's what we'll do. Here we go. New page. I've been trying to see, I've been liking OneNote, but the writing on it doesn't look good. And I think maybe I just need to make the cursor bigger than whatever it is right now, 0.5 millimeters. Maybe I'll try making those bigger and changing those. Maybe that'll help.
Yeah, it works much better with the thicker cursor.
All right. So
But
that's
I use an iPad, so that might be different too. So
do you use the OneNote or do you use something else?
I use OneNote on the iPad.
Okay.
For note-taking.
Well,
Maybe.
OneNote still has, there's two different versions of it. You still have the older version, or you can change to the version you're using. And the older version allows you to change the stylus a lot easier.
I was trying to research it because I've used older software and there's, they have these built-in features to smooth out your handwriting. And I feel like it's not in this one. And it's like, It's weird. It's like, that's old. That's really old stuff. And it's not in this newer program, I feel like. So that's why I was like looking it up. It's like, is there some add-in or something or something better? It seems like for Windows, OneNote's the thing to use. But I hate going to the old software because then you get deal with programs that just stop working, and you lose that compatibility. So no easy solutions to life. What are you gonna do? I guess if that's the worst thing I have to worry about, we'll be okay. So n equals 1 to infinity of 2n plus 3 over 3n plus 2 to the n. Is this convergent? Now, oh, I see. So this one is a little tricky. Let me see here. Is it clear? So what do you guys think when you look at this? And that's what you should always ask yourself, right? And I try to do that too when I'm with you guys. So, you look at this and do you think it'll be convergent or not? What's your intuition tell you? Give me some votes here. I'm going to close my door while you do that.
My guess is yes.
Yeah, why do you think?
I got a really strong convergent feeling with this one. The force is strong.
Why though? What's your thinking? What's your reasoning? And come on.
To me, it doesn't look like one of the ones that have been divergent, so then to me it looks convergent.
Does it look like something you know is convergent because you like write something maybe you think is similar to it that is convergent? Anything like that? No? Okay. Well, you know, to me, always thinking about what's it doing with the large numbers, right? You kind of always know, you know, if it usually it kind of approaches zero, then you're feeling like a lot of times if it approaches zero, we're thinking it's probably going to be convergent, right? Unless it's those P series that aren't. Which in this case it doesn't look like it. But I don't know. This one might be a little bit more difficult to see because if I'm looking at this, the limit as n approaches infinity, to me that kind of looks like 2/3. Like the inside will definitely, if it was just 2n plus 3 over 3n plus 2, it'd be 2/3. But we got 2/3 to the n. It's kind of like 2/3 the infinity. I'm saying, yeah, it looks like it's going to approach zero. But again, if I took the limit of this, okay, it equals 0, that doesn't prove it converges, right? And it still is like, well, I don't know. Is it getting close enough to zero or 2/3 of the n? Well, actually, 2/3 of the n, if it was just 2/3 to the n, that is actually a sequence we're familiar with, right? Take that back. What's 2/3 of the n? What kind of a sequence is that? Or series, if I threw that on there. What kind of series is that? How about Spencer? You know, don't you, Spencer?
Geometric?
Yeah,
Okay,
geometric, right? AR to the n minus 1. N is 1 to there. I think that's the one we're using for geometric. And in this case, A is just, well, it's close enough, right? Our common ratio would definitely be 2/3. It's a geometric. And so we know geometrics are convergent as long as that R is less than 1, between 0 and 1. So, so I would say, yeah. And I agree with Carly. Yeah, it looks convergent. I'd say because it does look very similar to this, but it's not exactly that, right? Could I use a comparison test? Comparison tests are so much fun. It's that easy to show is because this is convergent. Is this bigger than this? Well, the top, it's not clear if it is. Maybe I could show it is. Maybe I couldn't. I don't know. Well, the top is getting larger at a faster rate than the bottom. So this one is bigger than this. So no, I think looking at that, no, that's not going to be an option. So anyway, those are the easy options, right? We're looking at that. Well, I don't know. Are they easy? I mean, those are the ones we know already. But anywho, the root test. So we talked about that. Let's take a look at the root test. So we can use this test here. And, oh, let's do this. And then hit my clip. And just to give you guys the root test again, we've looked at this already. Oops. Escape. Move. Okay. Anyway, so we can use the root test here. There's no conditions on the root test. You just use it, right? And really, we want to use it when, well, look, we got this big ol' something to the n. That's kind of saying, okay, if I take the nth root of that, it'll kind of go away. And we can use the root test. We did a lot of ratio tests yesterday. This is very similar. So in our case here, we have a sub n is 2n plus 3 over 3n plus 2, all raised to the n. And so if I want the limit as n approaches infinity of a sub n, nth root of a sub n, and well, absolute value of a sub n. In this case, it's all positive, so we don't need to worry about the absolute value. And we're just going to use that formula there. If I take the absolute value, the nth root of the absolute value of all this is just going to cancel out with that n in the exponent, and we get limit as n approaches infinity of 2n plus 3 over 3n plus 2, which is child's play. It's 2/3. Okay. And then we can look, well, L, we are finding that L, and L is 2/3, which means L is 2/3, it is less than 1, which means the series is absolutely convergent. Therefore, the sum of a sub n is convergent, because if you're absolutely convergent, you are definitely also convergent. There we go. Kind of fun. I like all of these, though. Well, here we go. Okay, so find the orthogonal trajectories to the family of curves you see for any needed constant. Okay, so we have these curves here, whatever they are. X squared and y squared, they're conic sections, right? Well, we'll say equals something k squared. That's going to be some conic section. We're going to assume k is a constant. And we could plop this in, even in Desmos, put in a k and just see what kind of stuff do we get. If we want. But we want orthogonal trajectories. So what is an orthogonal trajectory? You guys know what orthogonal means?
They have to satisfy the slope.
What kind of slope?
The slope of the line we have.
Well, yeah, but oops, wrong button. Anyway, to this curve, an orthogonal line would be right here. That's orthogonal. Or a curve that would be orthogonal would be maybe, ooh, not that one. How about that one? That one's orthogonal. It's any curve that is perpendicular. The intersection at that point is perpendicular. Okay. So those are orthogonal. That's what orthogonal means. It means perpendicular, pretty much. So, and if we need to, we can look at some pictures and diagrams if you guys want. So how do you find a curve that is perpendicular to another curve?
Differentiate.
Yeah, you get the derivative, because what do we know about the derivatives at those points? They are inverses of each other, right? Negative inverses. Hopefully you remember that. So we got negative inverses. That's what we want. So it would be really, really helpful to know, well, what is the derivative of these guys? What's the derivative of those guys? So let's just differentiate, and I'll just do it implicitly. So derivative of x squared is 2x. X prime Oh, in this case, x prime is just 1. So it's 2x plus 4y, y prime equals, and that's a constant, 0. And then, of course, we want y prime. That's our dy dx, right? So we're going to solve for that guy. So we'll subtract 2x from both sides. And we get 4y, y prime is equal to negative 2x. Divide both sides by 4y. And I have found the derivative of this family of curves. It is going to be negative 2x over 4y. That is the derivative of any curve of this form right here. That's the slope at any point. For any point x and y. How are we doing so far? Is that okay, guys?
Yep, it is.
Okay. Okay, so what now that's not the derivative we want. We want to find a solution to a different differential equation. So this is a differential equation right now. We have, right? I have a
For the
function.
reverse of this?
Huh?
We have to just do the reverse, right? So x over 2y? 2y over x, I mean.
Yeah, exactly. We want to solve this. We want to solve y prime. We want to know when the derivative is the negative reciprocal of this. We want to find the family of curves that are orthogonal, that are, intersect perpendicularly to all the points of these curves. And so, yeah, negative reciprocal of this would be, now this is negative, so now we've got a positive, 2y over x. We want functions that satisfy this equation because we're looking for those orthogonal trajectories. Does that make sense?
Yeah, I remember now. I know how to do it now. You can move on to the next one. We just have to do the integration now.
Yeah. Yeah, now it's just exactly. It's like, okay, dy dx equals 2y over x, and, do our separation. So we could group our x's with our dx, our y's with our dy, and what I'll get is 1 over 2y dy is equal to 1 over x dx. And that way we can find the solutions here. Take the integral of both sides. I get ln of 2y. And I think that would be a half, actually, this time. Is equal to ln of x plus c. And we could solve for y here. And so I think our book does want us to. Okay, yeah. So let's see here. Multiply both sides by 2. I get, oh, wait a second. ln of 2y. Oh, I see what I did.
You could have just left the 2 on the right side, right? You could have just left the 2 on the right side and just carry out the y. Because it's just constant, it's going to come out. if you do it on the right side.
Yeah, I could have done a couple things. Anyway, let's just do with this. So anyway, this is fine. So we got ln of 2y is the same as, let's see here, 2 ln x. And, plus c, whatever. This guy, let's see, actually, let's do this. ln of 2y is equal to, and then we can use a property of exponents here if we want. ln of x squared plus c. And now we can exponentiate both sides. So, right, raise this to the e, raise this to the e, and I get 2y is equal to absolute value of x squared, which I think we can just write as x squared, times e to the c. Divide both sides by 2. We get y is equal to 1/2 x squared times e to the c. And you know what? This 1/2 and this e to the c can go together. I already did it once and just make that a different constant. So we can just say, you know what? Y is going to be plus or minus c times x squared. And that would be our answer. So there's the work for that guy. Is that okay, guys? Well, take that in. Would you like to see how this shakes out, like in Desmos? Would that help you guys to understand? Do you need a little visual for what orthogonal trajectories are doing?
Yeah, it might be a little helpful, I think.
Okay, well, let's do that. X squared plus 2y squared equals 14k squared. I'm going to go ahead and, anyway, where is it? It's this guy. Let's move this over. X squared plus 2y squared equals 14k. Yeah. Oh, see, that's a circle. Look at that. Or not a circle, but, a ellipse squared. There, still an ellipse. Like I said, it was going to be a conic section. And then here we can look at different values for k. So these are the kind of curves we're getting in this case, okay? Now what we found, what was our solution? Going back here, our solution was plus or minus cx squared. So let's take a look at that. And of course, plus or minus c, we'll just say cx squared. So, right, what's the plus or minus doing in this case? Not a lot. So we're going to say cx squared, cx. Here we go. Squared. And now you'll notice here that, see the parabola? And if we zoom in a little, where these intersect, those would be right angles. Anywhere this parabola, look at this, that's a right angle. And look at this, I can even change these, and it's still going to intersect. Everywhere it intersects is a right angle. So we found this family of curves, these parabolas, that happen to be orthogonal to this family of ellipses. Does that help? And then so in the review, you go, they're like, okay, what do these look like? Well, we just looked at it, this guy, right? We started with ellipses and our answers were parabolas. And obviously, we got cx squared. That could only be this one. But you can see in all of these, they're diagrams of orthogonal families of functions here. So that's that. It's office hour day anyway. You guys want to stick around and do another concentration problem?
I can.
Okay. It's up to you guys. Where were those? So, 9.3. Let's just check the homework here. Or I could even just find a problem for us. We can go through the homework or could find a problem. Oh, that was a similar one. And there's another orthogonal problem. Oh, this one's about beer and alcohol. That's more fun. Oh, and it's a little trickier. We got 6% is pumped in at a rate of 4 gallons per minute. And we got something pumped out at the same rate. What is the percentage of alcohol after an hour? So it's a little different. Because we're going with percentage, but so they're telling us the concentration this time. So it would be like concentration in minus concentration out. Oh, and see, there it is again, right? Rate in minus rate out. Concentration times that much, that would be what we're talking about. So we want to talk about the amount of beer. I'm sorry, the amount of alcohol. 16 gallons. Wow. All right. So anyway, let's go ahead and take a look at that. Where we go? Choo-choo. And we'll just set it up. Or we could solve it too, if you guys want to see more integral magic. So, here we go. We got a vet. The usual. We're putting something in. First off, we have 400 gallons. We got 4% alcohol. Oh, well, I guess we'll just write 4%. Beer with 6% alcohol is pumped in. So we got 6% times 4 gallons per minute. And the mixture is pumped out at the same rate, some percent, so some questionable percent is coming out at the same rate, 4 gallons per minute. What is the percentage of alcohol after an hour? I think I want to set this up the same way. Rather than do the percentage, again, let our function be the amount of alcohol. So we'll just say, let, how about A of t for alcohol? Let A of t be the amount of alcohol at any time t. There we go. And so the change in alcohol over the change in time is going to be the rate in minus the rate out. So how much is going in? How much is coming out? So let's see here. How much is going in is always is going to be that concentration which they gave us. So we don't need to figure out the concentration this time. It's 4%. Times, or no, 6%, sorry, times 4 gallons. So 0.06 times 4 minus the rate coming out. What's that? Well, that's this percent. You know what the percent here is? How do we find that? That's the amount we have at the time divided by the amount of alcohol divided by the amount of actual beer, right? Does that make sense? So in this case, it's the amount of alcohol at any time t, so that's A of t, divided by 400 gallons. That's the percent that we're looking at right here. That's coming out. Times, again, 4 gallons. So this is going to be A of t, or just A, over 400 times 4. And there's our expression for finding the amount of alcohol at any time. There's our differential equation. What do you guys think?
That makes a lot more sense now, the way you're setting it up with a problem that doesn't have a 0 for the rate in. Like I see your system for it now.
Yeah, and you always want to remember that rate is, and so in the other problem too, for, at least for the rate out, like we had to find the concentration. Well, I think we actually set up the concentration the same thing here. Right, and so you just got to remember, it's always that concentration, that extra little part, concentration times that rate. In this case, we had it right here. And it's the same thing over here. I definitely did a better job being organized with this one too. All right. Anyway, that's the setup. And then we can solve this guy and find the solution. And we will need an initial value. And we do have that. Kind of, sort of. This time, we don't know A of 0 right off the bat, do we? What I know is it's 4% alcohol. So it's 0.04 times the amount of liquid that's in there. So in this case, there's my initial value. I have to do a little bit of math first. And we use this at the end, right? So 0.04 times 400. Okay, 4 times 4 is 1600. Move back to 6, and there it is, our 16 gallons of alcohol at time 0. So we have an initial value. We have a differential equation. We can find a particular solution to this. Does that make sense? Okay. In that case, let us go ahead and we'll finish solving this. Or do you guys, do one of you guys want to do it? Want to tell me what to do? Let's see here. What is 4 times 0.06? It's 24.
0.24.
So yeah, 0.24. Minus, looks like
A is B over 100.
over 100. dA dt. And so it looks like, yeah, I think I'm good. I think I'll just move this over. So what? Add A over 100? No, that's not what I want to do. Ah, okay. Let's multiply both sides by dt. Is that okay, or do you guys want to do something else? Is there more than one way to do this? There we go. I separated my differentials, but my A is with my dt, and there's, you know, I don't want that. So I need to move all this over. That's fun. So divide by, yep, divide by 0.24 minus A over 100. Do that over here. And now, well, I don't know. What is that? That's just terrible. Let's multiply top and bottom by 100. Make that look a little nicer here. So times 100 times 100. All that. Okay. So we're going to get 100 over 24 minus A dA is equal to dt. That looks a little better. What do you think? Better?
Looks a lot better.
All right. And now we can take the integral. So now we integrate. Integrate. And what is this? I think I'm going to get a negative here. So wait. dA, yeah. Yes, so negative 100 ln 24 minus A equals T plus C. If I'm not making any terrible mistakes, that looks right. So you had to put that negative out in front because we have negative in front of our A here. So right, if you were going to work backwards, they'd cancel out and you did chain rule. Is that okay? So moving on, let's see here. We could say, hey, there's our function. We could do our substitution now. So let's do it right now. We had A of 0 equals 16. So remember that. We had A of 0 equals 16. So now we can go ahead and plug those in. We have negative 100 natural log of 24 minus what?
Would it be 0 then? Is that what you're...
Nope. Remember, I'm using this now. That's what I'm using here.
So you want 16?
Yeah. Minus 16 equals T, which is 0, plus C. So there we go. We got our C again really quick. Negative 100 ln of 24 minus 16. Is that 8? I don't need those absolute values anymore, obviously. ln of 8. That's our C. We plug that in. Negative 100 times ln of 24 minus a equals t minus 100 ln 8. And now we can solve for a. We can solve for a. And I guess, do we solve for a on this? So there it is. Well, I guess so. Let's do it. And then we can find that percentage. So we'll solve for a. Which means I would like to, what do I want to do? Divide it both sides by negative 100, I think. So we'll have natural log of 24 minus a is equal to negative t over 100 plus ln of 8. I think that's what I want to do. And then we'll exponentiate. So e to all this, and we're going to get, let's see, 24 minus a. Do we still need the absolute values there? A is the amount of alcohol at any time. Is it ever going to be negative? I don't think so. Couldn't be negative, right? So, and is it going to be more than 24? We're starting at 16. So I think we'll be all right. Take that out. So we'd have 24 minus a is e to the negative t over 100 times e to the ln of 8 which is 24. Let's see. This is positive. This is positive. Okay. 24 minus a equals 8 e to the negative t over 100. So we have negative a equals 8 e to the negative t over 100 minus 24. So we're going to go ahead and, oops. We're going to say a then must be negative 8 times e to the negative t over 100 minus 24. Oh, plus 24. There it is. Now that's the amount of alcohol we have at any time, right?
Yes.
24 minus E. Oh, so wait, 24 minus Y? Did I have 24 minus Y? Oh, yeah. Yeah. Okay. Oh, yeah. We're good. Okay, what did I just ask? Oh, yeah. So, what'd you say? Yes or no? Are we done? That's the amount of alcohol, but it was asking for the percentage after an hour. So what are we talking about? Are we talking about hours? We're talking about minutes, right? So what we need to do for the percentage after an hour, and I won't finish that. I'm sure you guys can do that. Percentage after an hour, but you'd want to pay attention to this since it's asking for not the amount, but the percent, the concentration. That was going to be our A of 60, the amount divided by, again, the total amount of liquid in there, which is 400. So if you want to find the actual answer, that's what it would be for what it was asking for. There we go. So that was a fun problem. That's a more complicated one of those mixture problems. Anything else, guys? Okay. Oh, yeah, Carly?
I was just going to say that was good review for me, so thanks for that.
Oh, good. I'm glad. Okay, guys.
Me too. Have a good one, Mr. Powers.
All right, thanks, you two. I will see you later, and I'll get this posted in a bit. Good luck, guys, on your studying this weekend. I'll try to be available, too. You got questions, let me know.
Thank
Okay.
you.
Thank you,
Yes.
Mr. Powers. Have a good
Got
day.
it. Thanks, you too. See you later.